Okay, good afternoon. Hello and welcome to this A2EP webinar on electric options for storing and supplying decarbonised industrial heat. My name is Laura Taylor and I am the Communications Manager with the Australian Alliance for Energy Productivity, or A2EP as we like to call it. Today I am joining you from the lands of the Jarrod and Guringai peoples in northern Sydney, and I pay my respects to their ancestors and elders past and present and acknowledge their heritage. If you would like to acknowledge the traditional owners on the lands from which you join us today, please, you can add that into the chat window. This webinar today is brought to you by our more than 90 A2EP members, a broad cross-section of energy industry leaders who share our mission to decarbonise and improve the energy productivity of our industrial and commercial sectors. From the A2EP team today, I'm pleased to be joined by our CEO, Jarrod, who will be stepping in later in this webinar to lead the panel discussion after the presentations. Before we go any further, just a bit of housekeeping for the webinar. First of all, the webinar is being recorded, so you can just sit back and relax, and all the registrants of the webinar will receive links next week to the recording and also to the slides from our presenters today. Also, secondly, time permitting, we will take a number of questions at the end. We'll take the questions after all of the presentations have finished. You can enter your questions into the Q&A window, and even during the presentations, if possible, our presenters will actually respond to those if they can, if that's applicable for them. Here at A2EP, we're really excited about what we see as the significant potential for our electric thermal energy storage, or eTES technologies, to facilitate the decarbonisation of industrial heat in Australia. Through our boiler and burner mapping project in 2024, last year, we discovered large energy users were actually looking to electrification to decarbonise their industrial heat. And these technologies that we're discussing today can absolutely serve that electrification pathway. They can soak up that low and negatively priced renewable electricity from the grid to decarbonise their heat. But at the same time, these technologies also offer grid benefits by helping to balance the increasingly dynamic electricity grid and also increase network utilisation. These technologies are real, they're proven, they're here and now stuff that can have a really big impact. So to just explore the potential of these technologies, we've brought together a fantastic panel of presenters for you today. I'm happy to be joined by Askell from Essential Energy, Tom Geiser from Rondo Energy, Furness from MGA Thermal, and Reeves from Arena. First up today, I would like to introduce Askell from Essential Energy. Ian has more than 20 years' experience working within the electricity industry, including demand management, strategy, and innovation. As the Senior Commercial Specialist, Electrification and Key Accounts at Essential Energy, Ian's responsible for the development and implementation of Essential Energy's electrification program for business and residential customers. And Ian will be sharing the DNSP perspective on eTES technologies. Ian, would you like to share your presentation now, please?
Thank you.
Looking good.
We can all see. Fantastic. Yep. Thank you for that warm intro, and thanks for the opportunity to present today. So today I'll just provide a quick overview of our program and focus on industrial decarbonisation as part of our electrification program. Before that, though, if we just recap Essential Energy's network footprint. So we cover 95% land mass New South Wales, basically all areas outside of Sydney, Newcastle and Wollongong. Currently today we have connected about 2.2 gigawatts rooftop solar PV. So this is both the mums and dads with solar panels on rooftops and small businesses, as well as another 1.5 gigawatts large-scale renewables. So and as a result of that, we're operating about a third of our network at zero carbon in the middle of the day. So the purpose of electrification programs is to support our customers on a least cost path to decarbonise. And we're aiming to do that through increasing network utilisation. So another objective of our program is to support the efficient use of the network, which will result in downward pressure on network charges, effectively reducing the dollar per kilowatt hour of energy delivered through the network. And I should say our program is very much focused on the decarbonisation of non-transport fossil fuels. So they're things such as LPG, natural gas, coal and diesel, which definitely sings to the topic today on industrial decarbonisation. We also have an EV strategy I won't talk about today, but that deals with on-road transport decarbonisation. Just in terms of setting the concept, in terms of industrial emissions, but this is a New South Wales focus, noting it Essentials Network we service within New South Wales. The Productivity Commissioner for New South Wales actually released a report just late last year on industrial emissions and in terms of reaching our net zero targets within New South Wales. And there was some concern raised that the industrial sector is not moving as quick as it should to meet the targets. It's a great report. I do recommend reading it. But in terms of in terms of total New South Wales emissions, the reason why I'm bringing this up is that if we can really come up with solutions and work together with industry, try and accelerate decarbonisation of industrial process heating, we can really move the dial on emissions. And this would be the same across other states. And I should also reference the ARENA report. Most of you on the call may have read that report back in 2019 for options for industrial process heating, which they called out that about 91% of energy used today for industrial process heating is above 150 degrees. So that's above typically what a heat pump can service, which I know Jarrod's more qualified to talk about that than I am. But basically this sings to the solutions and the technologies that will be presented today in terms of eTES type units to try and come up with solutions to decarbonise majority of process heating. Just quickly capping to set the context, there's some major changes happening in three critical areas I just want to call out. So in terms of the national electricity market, there's significant changes in terms of the energy mix, which is influencing both the cost of wholesale energy, where we're seeing now even negative pricing during peak solar PV production periods, but also the rapid decline of the carbon intensity of New South Wales, or I should say in the NEM, the National Electricity Market energy during peak solar PV production times. But we are seeing a rapid reduction during those times in terms of the carbon intensity of energy in the market, which I'll talk about later on. We're also seeing a rapid advancement of technology. So we've got two technology providers on the call today, which fairly simplistic technology in terms of how it operates, but I'm very excited in terms of the technology and how it can interface to networks and to the market to really sing in tune to intermittent renewables. So effectively then looking at, if we move around further clockwise, digitisation of the market and networks and the connecting load and generation is really enabling a significant opportunity here to accelerate industrial decarbonisation, which I'll talk about that later in the presentation. So just to talk about carbon emissions, and again, this is the New South Wales focus, linked to our program and in terms of the New South Wales carbon intensity of the New South Wales grid, which this figure presents the forecast carbon intensity, which by about 2030, early 2030s, is forecast to effectively be zero carbon, driven by the rapid change in energy mix in the market. If we look at the carbon intensity during the middle of the day, so during peak solar PV production times, already at a New South Wales or a state-based average, we're already operating in terms of late 2029. But as I mentioned before, for about 1/3 of our network, already today, we're operating where the average New South Wales grid would be in the early 2030s. So that's a key piece I just wanted to call out, is that with the rapid uptake of renewables, which we're looking at supporting even more, depending where you're connecting in the grid, you could already be operating at zero carbon. So taking that previous figure, which is this red curve, is the forecast carbon intensity, and we overlay both LPG and carbon intensity of LPG and natural gas. So this is a kilowatt hour per kilowatt hour consumption. You can already see that during the middle of the day in New South Wales average, it's about on par with LPG. But as I mentioned before, for about 1/3 of our network, grid served energy is much, much less versus gas, both LPG and natural gas. When we compare the electric machines, so we have to consider the efficiencies at which they operate at. So in this instance, the yellow curve, I've looked at an eTES and compared it to a boiler, a gas boiler, which I was probably a bit generous. I gave the gas boiler an 80% efficiency and the eTES unit about 90% efficiency. And this is comparing the input carbon intensity in terms of this is using grid served energy to deliver the same heat energy. And as we can see, again, in the middle of the day, we can operate that machine at much lower at slightly lower carbon intensity compared to LPG. But if we consider where it plugs into the network where we have reverse power flows, if you electrify today, you can already operate at much lower carbon intensity compared to gas and LPG. So that's to talk about carbon intensity. So already there's higher temperature applications today for decarbonising industrial process heat that's operating at lower carbon. If we talk about energy costs now, which I'll talk about electricity costs, and then I'll talk about, wholesale costs, sorry, and I'll talk about network costs. So this figure presents the average New South Wales wholesale market. So 365 days averaged, which we're already seeing just over the last year, energy prices during peak solar PV production times around $30 to $40 a megawatt hour. I should mention, if you remove, say, the 10, 20 peak days in the year, you can actually get this wholesale price down a lot lower. And some business cases we're working on already in New South Wales, we're effectively seeing wholesale costs are averaging out around zero. And it's different in each state, and I think Tom will talk about that later in terms of those opportunities. But just as a comparison, I've overlaid the retail cost of gas on a megawatt hour basis. For instance, the $25 a gigajoule, which is typical for LBG customers in our network footprint. Already you can see that is higher costs on an energy basis versus wholesale cost electricity, and even so for lower cost retail for gas. So all I want to call out on this slide is, with the rapid changes in the wholesale market, energy cost is getting cheaper, driven by the uptake of renewables, and this is presenting an opportunity to reduce energy cost. So now moving on to the network costs component, which we're actually working on a trial of some industrial customers around innovating connection access and tariff design. I just want to talk to the concept of increasing network utilisation and how that reduces network costs. So this figure presents a low duration curve, which a way to think about how this is generated is basically we can take 30-minute snapshots over a whole year in terms of the total network demand. We sort it from largest to smallest. So this presents our total network, which our network peaks at about 2.5 gigawatts. Peak demand is a very strong correlation between peak demand and the cost to serve. And the reason behind that is peak demand, obviously, it's driving the physical size of those assets, so the size of the transformers and the conductors. So if we can manage peak demand or deploy demand management techniques when we connect new load, we can actually avoid what we call network augmentation. So we don't have to make the networks physically larger, and then we can avoid that additional cost. But in addition, how we collect our revenue, we operate under what's called a revenue cap, which is linked to the physical size of our asset base. So if we can physically cap or manage peak demand and not increase our asset base, our revenue remains the same. But if we can add more load and increase energy throughput, we can effectively reduce the unit cost of accessing the network. So theoretically speaking, say we double the energy through the network and not increase the RAB, the regulatory asset base, we can effectively halve the unit cost of the network, which is a great outcome for businesses and also the mums and dads connected to the grid in terms of lower energy costs. So I'll now move on to one of the examples of demand management in terms of managing peak demand on the network. One of these methods is our future network engineers are currently working on a new connection standard called dynamic access to network capacity, or dynamic operating envelopes, which basically it's signaling real-time capacity in the network, which is a significant shift from our static connections for load and generation we have today. And it's enabled through, as I mentioned before, around digitisation, so enhancing visibility in the network, but also the ability to be able to signal to load and generation in the network that can respond. That's enabled through digitisation. So in this example, this is an industrial feeder linked to an industrial precinct, which already for instance, there's a low duration curve where we're experiencing about 3.5 megawatts peak demand on the network. But as you can see, outside of that time period, there's a significant amount of asset capacity that can be utilised. So we're currently working in developing a trial to signal that spare capacity on a real-time basis for an eTES unit to be able to soak up that spare capacity. And I should also mention that peak load is near the capacity limitations of the feeder. So without this type of connection arrangement, we would trigger a significant investment in the network, which would basically it wouldn't be feasible to connect that load to the network. So another way we can drive network utilization, increase network utilization, is by signalling through our pricing, so our network pricing. To explain about that concept, basically taking a summary of the national electricity market, so traditional market in terms of generation, transmission, distribution, and the end customer is connected. And I've expanded the distribution network into components that make up our network pricing. So we typically split into 3 components. So sub-transmission, so that's 33,000 up to 132,000 volts in our network. The high voltage network, which is 33,000 down to about 11,000 volts. And then there's the low voltage network. So this is typically in the street, operating the 415 volts 3-phase. So in terms of cost to serve, there's asset classes linked to these voltages, which then determines pricing. So depending on the supply path, a customer using the network determines the cost to serve to deliver energy to that customer. So just on the last slide, if I just mention about the trial we're currently setting up with some industrial facilities to support the connection of highly flexible loads, we're seeing areas of our network, as I mentioned, with reverse power flows. So we're currently working with our network pricing team and with the providers of this technology as well that's highly flexible, to establish a trial where we could signal basically in a sun soaker period. That's when we have significant solar PV in the network, together with a dynamic operating envelope. If we're only using the local area of the network, then we could signal a very low price that's linked to the local use of the network. So effectively a very low rate, which indicatively what we're looking at this stage is effectively an off-peak rate. So it could be much less than $50 a megawatt hour, which if you stacked it together with the wholesale pricing, we can already see that electricity is lower cost than gas. But I should mention this is a trial tariff that we're currently working on, and we can share updates of that as that trial progresses. And then just lastly, I just wanted to mention around electrification program. So we are supporting co-funding feasibility studies of representative customers per sector, and this involves trials as well. So just wanted to do a quick call out that if you're interested in your industrial facility across the central energy network footprint and you'd like to participate in our electrification program and support lower cost methods of decarbonising, please feel free to reach out. Thank you.
Excellent. Thank you so much, Ian. That was really great scene setting for these technologies and the opportunities for them to succeed. Now it is time to move on to the technologies, and I'm very pleased to introduce Tom Geiser, who is Head of Australia for Rondo Energy, and they are the makers of the Rondo heat battery, which some of you might have seen presented at the Australian Renewable Heat Conference in September in Sydney. Tom has more than 15 years experience in the electricity sector, in spot trading, operations, retail, regulations, and commercial. So Tom, if you would like to please share your screen.
Thanks, Laura. Is it working?
Control L.
How's that?
Beautiful. Thank you.
Okie dokie. Hi, folks. So my name's Tom. I'm just going to be chatting a little bit about what is eTES, electric thermal energy storage. So the fundamentals, if you have any material, pretty much any material with a low vapor pressure, so that's something that doesn't boil, so water is out, you can store huge amounts of energy just by heating it up to a high temperature. So this could be like dirt to rocks level of stuff up to fancy materials. Most things have a pretty decent heat capacity, and you just need to find something that survives high temps without creating a large pressure. There is a trade-off between how cheap your material is and how it performs. So dirt is dirt cheap, but it has dirt performance, and that is going to have cost implications for how your system is integrated and footprint and all of your ancillary costs. Why would we do this? Well, first of all, storing heat is a lot cheaper than storing electricity, for instance, or chemical energy. It is also a lot more efficient. So we can simply store more for less money. That's nice. Okay, why would we store in the first place? And Ian has alluded to this already. Basically, we're at the point where if you directly electrify baseload electricity is going to cost more than fossil fuels in many circumstances. Being able to buy just in the off-peak gets you significantly cheaper electricity to the point where it's competitive with fossils. That's why we're doing this. So what is Rondo's version? So I'll just stop for a second and show you, do a little bit of a show and tell. So oops, it's a bit blurry. That's a sample of our brick. It's a lumen silicate brick. It's used in electric kilns or any kind of kiln, basically, as just a interface. It's tough and cheap. That's some of our heater wire. It's iron with a little bit of aluminium in it, so you get a nice oxide coating and it doesn't degrade at high temps. Oops.
Could you just speak up a bit, please? It's a bit hard to hear you.
Sorry.
That's okay.
Zoom doesn't like me for some reason. Let's go. Okay, so we have a bunch of bricks. They're not tiny bricks like that. They're actually quite large. We have a bunch of bricks in a stack with resistors, and we are taking electricity into those resistors. It can be from the grid. It can be, we have projects where we're building completely off-grid systems, and we have systems that are only connected to the grid and buying electricity from far away. And we have combinations where people have a generator located close by, but they're also using the grid to supplement. So we're charging flexibly based on the resource or based on prices, storing a large amount of heat, and then we have a second control system that is blowing air through that stack of bricks to deliver heat to the specifications that the customer needs. So their SCADA system can communicate with ours and demand basically like a steam, pressure, temperature, flow rate, that kind of stuff. It's 95% plus efficient, very good. That's pretty much, I mean, not other kinds of storage are just not going to get close to that. So here's a couple of, like a 3-day example of how you might see a heat battery operating. So this is our small unit. It's delivering 7 megawatts of thermal energy on a continuous basis, and it's charging up to 20 megawatts electric, just when prices are cheap. So you can do that quite flexibly. You don't have to do it in big blocks, but it just happens that's how the pricing was. And you can see while we are charging, the state of charge of the battery is increasing rapidly, and then when we're not charging it, it declines slowly until we have to charge all over again. Worth pointing out, we're charging and discharging at the same time. That's a trick a regular battery can't do. What is Rondo up to around the world? So Australia is our newest region. Elsewhere in the world, we have 2 projects under construction. We have a demo project that's been in operation for a bit over a year. And we're going to start construction on a few new projects, primarily in Europe, and more of them are in execution phase. And we have a partnership with a Thai company called SEG. They have a ceramic subsidiary, and they're the producer of our bricks. We can produce 2.4 gigawatt hours per annum, and I think we're at about a third capacity or something like that at the moment. So why are we in Australia? Basically, the wholesale prices are good. You can get access to them as a large consumer, and it's pretty remarkable how good they are relative to the cost of gas. Okay, so Victoria, I've kind of chosen a good example. It proves the point. It's not as good as this everywhere. This is a distribution of price from lowest to highest across an entire financial year. So I've cut the graph, otherwise we can't see anything. Price can go as low as negative 1,000, but it doesn't do that very often. And it can go as high as 16,000 or over 16,000. That keeps increasing. So there is quite a lot of volatility. I've got negative price 20% of the time, the average without network costs is about the same as gas and carbon. So once you factor in all of those extra costs, it kind of doesn't make sense. This is one of the best states and a good year for price. So 24/7 purchasing doesn't quite make sense. Okay, but what if you don't do 24/7 purchasing? So we ran a dispatch model across this data with the constraints of how the battery would operate. And we can get a average dispatch price across the year of $1 a megawatt hour. In gas terms, that's like, I mean, it's practically free. So it's silly to say, hey, it's 50 times cheaper than gas. It's just very low. If you reduce the utilization of that heat battery just a small amount, you can actually get to a negative number. So I think Ian mentioned this as well. If you're prepared to keep your gas or LPG backup, run it a few days a year, you can get to a net cost of zero operating cost, which is pretty remarkable. When we're looking at the other states on the East Coast, SA and Vic are by far the best in terms of the off-peak price. There is a big separation between the north and the south. Queensland, New South Wales are a lot more expensive. New South Wales, definitely the worst in terms of off-peak prices, although it is getting better. That probably has the most development for new renewable assets that are going to push that down, whereas not that much happening in South Australia, for instance. Tasmania is quite flat because of all the hydro. They already have flexibility, so they don't need significantly more flexible assets. So just let me dream here for a moment. If we look at, how good is this flexible resource for the network as a whole? So roughly East Coast industrial heat demand is about 10 gigawatts if you electrified everything. If you ran that off a heat battery, that's going to be something like 30 gigawatts of flexible load, which is bigger than all of the dispatchable generation sources in the ISP. And you'd get back a small fraction of that as electricity if you've got some combined heat and power in the mix there, which would be nice to have. What does that change in terms of the equilibrium of these resources? Well, we're absorbing more of that curtailed energy, so there's a more profitable equilibrium for renewables. You can build a bit more of them, and that means you don't need to store quite as much energy. So we're getting other capital savings in the rest of the system. And other nice stuff like regional development. It makes sense to locate these, for instance, in renewable energy zones, and value add on things like minerals and agriculture, which we're good at, but don't really value add. Thanks. I'll stop there.
You caught me unawares, Tom. That was a very sudden end to the presentation, but that was fantastic. Thank you very much. And we've already got a few questions coming through in the chat window and in the Q&A window. So Tom, you might like to respond to those if you can over the next while, but we will have more questions at the end of all the presentations. Just on the technology side of things, let's keep that going now. I'd like to introduce Will Furness from MGA Thermal. Will is the head of business development at MGA Thermal, where he leads the go-to market strategy, global pipeline activation and growth. Will, if you come off mic and share your presentation, please.
Yeah, hi Laura, you can hear me well?
Perfectly, thank you.
Okay, great. That should be coming up as we speak. How's that?
That's great, thank you.
Great, awesome. Okay, fantastic to be here today speaking with you all, and thanks to A2EP for organising this event. There seems to be a bit of a groundswell with thermal energy storage in industry at the moment, so it's great to have events like this where we can get a good cross-section of what's going on in the market. As Laura said, my name's Will Furness. I'm the head of business development at MGA Thermal. And I guess what we're starting to see is we're really on the cusp of this industrial renaissance. It's about a quarter of the world's greenhouse gas emissions are sourced from industrial heat, and 90% of that industrial heat is sourced from fossil fuels. So although there's a lot of room for incremental improvements in process efficiency, and that's really important, we still have a need to transition away from expensive fossils. So we really need breakthrough technologies that are going to transform industrial heating and, importantly, that offer a really compelling value proposition. So I guess MGA thermal, our solution is about reliable, economic and clean steam at scale and up to 550 degrees Celsius. So how do we do that? It's really a firming technology. So we charge using that intermittent least cost off-peak renewable electricity. We store that energy as heat in our proprietary blocks, and I'll come to that on the next slide. And then we deliver reliable heat and power on demand on a 24/7 basis. So key verticals that we're targeting are really chemicals, oil and gas, minerals processing, food and beverage, and building materials as well. So how do we get to that? Well, so what you can see on screen at the moment is a cross-section of one of our proprietary MGA blocks. Each block is about the same size as a shoebox, so 5 litres, 10 kilos, 1.5 kilowatt hours of storage per block. And it's made of a graphite matrix with dispersed aluminium particles, and that's what you can see glowing red hot in this image on screen. Now, I guess these blocks have been designed from scratch with the desired properties for thermal energy storage, and that's really a focus on economics, conductivity, energy density, and longevity. And uniquely, these blocks, they embrace the benefit of a phase change while being outwardly solid. So that's that aluminium particle, which melts as we heat our system up and then cools down as we dispatch energy, all the while staying secured and encapsulated within a solid graphite block. If we then step back to the system level, during charging, we use electric resistive heating elements to convert electricity to heat, and then we absorb that heat using our MGA blocks inside of an insulated enclosure made of mild steel. And then during discharge, we use a closed cycle nitrogen gas loop to transfer that heat from the blocks to an off-the-shelf HRSG to generate that high-grade process heat at up to 550 degrees Celsius and well over 70, 80 bar pressure. And I guess there's a couple of key flow-ons from that. So the first one, and a really key tailwind for thermal energy storage is energy density. To give you a number to pin to, lithium-ion batteries have 24 times higher energy density than MGA thermal storage solution. The second point around rapid heat transfer, part of the reason we use a graphite matrix is because it has really high thermal conductivity, and that rapidly distributes heat through the system with low thermal stress so that we can get energy in as quickly as possible at least cost, and then dispatch as quickly as possible on demand. We use a large-scale industrial engineering approach, and that ultimately gives us really good economies of scale, as we start to go beyond 30 megawatt hours, even up to gigawatt hour storage capacity for some of the sites that are in development. Simultaneous charging and discharging, really important for flexible operating modes, including 24/7 output. But as Tom and Ian have already pointed to, having these highly flexible assets in the grid is going to be really important to uptake and adoption. And then lastly, replacing key equipment in service, particularly our heating elements, with uninterrupted operation. So I guess we're trying to think about, not just the development of high performance thermal storage materials, but from an overall system design perspective, how do we maximize value to customers and then ultimately allow us to deploy these assets in a streamlined and accelerated way as well? We understand this is a show me, don't tell me industry, and I'm actually super excited to share. We're currently in hot commissioning for our 5 megawatt hour pilot project, which is in Tomago, New South Wales. So it's a shame, Ian, it's just outside of Essential Energies network. We're actually in the Ausgrid network, but that's actually on track for completion in the next fortnight. So we're really close to that. And thank you very much to Arena and to Shell for funding support for that project. This is a really critical milestone for our technology readiness. And actually last week, I mentioned we're in hot commissioning last week, and a very real milestone for us, lifting the maximum operating temperature of our unit up past the phase change temperature, and then dispatching superheated steam at 360 degrees Celsius and 40 bar. So really testing the upper limit of this unit last week, which is super exciting. And I guess the long-term purpose for this demo unit, is really about knowledge sharing. It provides an opportunity domestically here in Australia for stakeholders to come and get your hands dirty with this unit in our sandbox environment. And the performance data from this unit, which will be, a level of that will be publicly available, will ultimately help to promote the business case development for thermal storage here in Australia and abroad as well. Economics, really critical to adoption. And I guess the good news is today, thermal storage is already economically competitive with fossil fuels and competing renewable technologies on an LCOH basis. I guess further to that, we're actually expecting a 30 to 60% cost out of the capex of our system as we scale up. That addresses that navy blue chunk down on the bottom left of the screen on the MGA TES column. But I think, and we're going to turn to some case studies on the next couple of slides, there's actually significant potential upside that can be enabled through thermal energy storage, which is not reflected here in this straight displacement of gas with least cost renewables. Thermal storage is a highly flexible, scalable energy storage asset that can actually drive a step change improvement in the overall process efficiency of sites. It can actually enhance energy security and resilience of those industrial sites. And as Ian has been talking to, it can actually provide grid services as well. So I think what we're finding is we're working through a lot of the feasibility studies with large industrials is that these upside opportunities are seriously moving the needle on the business case for TES and making it a more immediate term prospect. So let's turn to that now. Now, we have NDAs up to our eyeballs at the moment, so I'm going to be anonymizing these case studies, but just want to highlight some of those benefits I was alluding to. This first case study, an off-grid mining and minerals processing site that currently uses gas-fired package boilers for their steam production. The steam is used for their digestion and drying processes on site, but it's actually also used for backup power generation using steam turbines. So I guess part of the problem that they're facing on this site is these package boilers are really not flexible enough for their operation. So for energy security reasons, they need to run these package boilers 24/7 idling on minimum turndown, which for context is 20 tons per hour of steam, so significant energy load. And they do that on minimum turndown ultimately so that they can rapidly ramp up steam generation in the event of a contingency. That 20 tons per hour is not being used on site, it's simply exhausted to atmosphere. So it's a massive source of energy consumption and waste heat. Now, when we look at thermal energy storage, we can ramp up steam generation rapidly, about 25% of nameplate capacity per minute. That's far more rapid than traditional or incumbent package boilers. And ultimately, that means that we can turn those package boilers off minimum turndown to hot standby, saving that 20 ton per hour of steam demand, and use our TES unit to respond rapidly to any contingency event that occurs. So that in and of itself drives a 13% reduction in the annual steam demand from the TES, so a significant chunk. The next example is a building materials site. So I guess for this site, there's actually a significant amount of low-grade waste heat that's currently exhausted to atmosphere due to some operational constraints. They don't currently have a way of recovering and utilizing this low-grade waste heat. It's too low temperature, low pressure to be utilized directly in other processes, and so they currently exhaust that to the atmosphere. Now, in this case, we can actually use our thermal energy storage to produce really high temperature, high pressure steam, and we can use that to boost the quality of that low-grade waste heat to sufficient pressure and temperature so that it can be used on site. That delivers a significant improvement in the overall process efficiency of the site. It's about 10% of process efficiency, and in this case where we are, sorry, I should pause on that because it is a significant chunk. 10% improvement in process efficiency. It's significant, and it's starting to move the needle. the next point, I guess, is on grid services. So this will be a grid connected application, and given the flexibility of that asset, Ian, you were talking before about some of the reverse power flows you're experiencing in different parts of the market. Some of the capabilities of TES start to unlock some of those additional revenue streams through grid services as well. Great. And then so I guess second last slide here, just regarding our traction to date. So we just announced our first paid feed study with Chevron Energy, Fortune rated company, to complete, I guess that's for a 5 MWh trial unit for one of their sites in North America. That was delivered in collaboration with Anacapa Engineering, so Chevron's appointed EPC. There's another project which is in development at the moment, 180 MWh deployment, which will be in Western Australia for an industrial zone asset, where that will essentially be feeding steam over the fence to multiple offtakes, with a consortium involved in that pre-feasibility study. The consortium involving an energy company, engineering, consultancies, off-takers, and funding and asset owners all lined up for that. So that's super exciting. And then again, thank you to Shell for their support, who provided about $400,000 to support our demonstration unit, which is coming online next month. So yeah, some really exciting milestones coming up for us commercially as well as technically. I guess maybe to close and wrap up, I just want to reiterate that point at the start, that we're really on the cusp of an industrial renaissance. Thermal storage is more than just electrification. It's a highly flexible, large-scale storage asset that can drive a step change improvement in overall energy efficiency, reliability, security, and sustainability. And we're finding, particularly as we dive into the detail with a lot of industrials, that's what's really moving the needle. So whether you're interested from a collaboration or a client perspective, I really do welcome your contact, and thank you again to A2EP for having us.
Excellent. Thanks so much, Will. Another look at some really cool, or should I say hot, technologies. Now we come to another Will, and last but certainly not least, because he's the one talking about the money, we have Will Reeves, who is an investment manager in the business development and transactions team at ARENA. Will focuses on ARENA's low emission metals portfolio, as well as industrial decarbonisation as part of ARENA's delivery of the Powering the Regions industrial transformation stream. Will, if you'd like to come off mic and share your screen, please.
Awesome. Thanks, Laura. And just echo Will's comments on thanking A2EP for organising this and the other panelists' presentations thus far as well. I'm just going to make sure that can be... Is everyone able to see that? Okay.
Yep.
Awesome.
That's great.
So yeah, as Laura said, thank you so much, Ian, for providing some market context, and then Tom and Will for kind of drilling down into the technological aspects. But I'm sure there's some questions on exactly what are the funding options available today. And so yeah, really excited to talk to you about our industrial transformation stream program. Before jumping into that, I'm sure a lot of you are broadly aware of what ARENA does and ARENA's purpose, but as a quick refresher, ARENA was established in 2012 with a purpose to support the global transition to net zero emissions by accelerating pre-commercial Australians to the pre-commercial innovation to the benefit of all Australians. Our CEO likes to use GERTRABAR as an acronym, but it's not the sexiest one, so don't use it too much. We enable that transition by providing financial assistance in the form of grants, and in return looking to get knowledge sharing, so that kind of information and learnings can be disseminated to the rest of the industry. So specific to ARENA's journey in industrial decarbonisation, beginning of 2023, the 1.9 billion Powering the Regions Fund was announced, and within that, ARENA was tasked with delivering the 400 million industrial transformation stream program. And so that was focusing on existing regional industrial decarbonisation, of which I'll touch on in the next slides. I think key call outs here and how it differentiates to other funding options available, such as the STS and CERSI funding. Within ITS, we have a bit more of a broad scope mandate and, can consider several process heat options within that, can look at scope 1, but also importantly, scope 2 emission reduction as well. So that allows us to look at common user infrastructure and then also have a technology agnostic element to that as well. The program objectives are relatively aligned with existing ARENA programs and yeah, really focusing on that industrial decarbonisation offtake piece, how this will kind of be commercialized, and that kind of links into the program key features. So by definition, the industrial transformation stream program is aimed at providing projects that are to the direct benefit of an existing ENGA controlled facility in regional Australia. So regional Australia as outside of the capital cities, but including the Kwinana, and then industrial activity ranging as on the slides there. But I think obviously the kind of broad applicability of the thermal storage or eTES within the overall process heat shows that our focus on that is well and truly aligned. In terms of the program itself, unlike other ARENA programs, it's kind of like an open program with a series of time-bound focus rounds. Round 1, which had an explicit focus on process heat decarbonisation, launched in December 2023, and we're looking to launch round 2 in March 2025. Again, really interested to consider thermal energy storage options within that. And I think a key piece to call out here is within the 2-stage ARENA application process, it's really meant to be a collaborative exercise. My role in the business development and transactions team is to kind of be like the front door to the ARENA process and guide applicants through that stage. Merit or projects are assessed on a 5 key merit criteria, which we would walk you through. And I think the key piece to call out there is that we are looking for projects that have an emission reduction benefit absolute within the project itself, but then really understanding what is the broader applicability of this technology. And so that means that a smaller project isn't viewed any less favorably than a larger project. And it's all around the what is the upside and kind of commercialization potential of these technologies. That is kind of the key overview. Key documents are on our ARENA website. As Will said, I would really welcome anyone to reach out with potential questions or funding options as well. And again, thanks to Jarrod and Laura for facilitating the discussion.
Awesome. Thank you, Will. That's really great. A great overview and reminder of what's available from ARENA, and it is a lot. And just to sort of reiterate what Will was saying, if you're interested in developing a project, do get in contact with ARENA because they're very happy to provide feedback and support to you as you're considering that and considering what funding to go for and what technologies to look at. So that's great. Thank you, Will. And now it is my turn to hand over to Jarrod Leake, CEO of A2EP, who will be carrying the question and answer section of this discussion. Thank you, Jarrod.
Thank you so much, Laura, and to our speakers. The questions are lighting up, so let's see how we can go getting through them. I'll kick off with a couple that I might answer, then we'll get the panel involved. One question was about heating up such technologies. What heat sources can you use? I understand both of ours today were electrically heated, so you're using what Tom showed with that electric resistance wire, just like I guess what you've got in your toaster. There are other technologies where you would heat them up with external sources like from solar thermal, and that would be things like Energy Nest. They use more of a solid concrete block with some metal tubes going through that and heat up that block with, say, solar thermal and then draw on that, say, overnight. So that's other tech like Energy Nest for that one. Tom, I saw you answered a few questions there from Alex Holworth. We'll just dip into those. The max operating temperature, Tom, you had 1,000 to 1,500 degrees. Is that the delivery temperature as well?
It can be. That's what we're aspiring to get to, that 800 plus range for calcination processes. At the moment, I'm just chasing steam stuff in Australia. It's very easy to integrate by comparison. but we're looking at high pressure and high temperature applications for that as well. So like if you can make power that's already high pressure, high temp, and so
Gotcha.
CHP is my favorite. I haven't got any of those yet in Australia, but we have some overseas, and that is you taking high pressure, high temperature, drop it through a turbine, and the waste heat is your process heat for the customer.
That would be nice. Get electricity and heat back. Okay, working on that one. Will Furness, MGA, what's your max temperature there?
Yeah, thanks, Jarrod. So we dispatch steam at up to 550 degrees Celsius. So I guess similar to Tom, we're really pursuing steam use case at the moment. It's not all steam. That's probably about 95% of the opportunities we're looking at. There are some other opportunities where we look to provide hot air or other gases. But I think below 100 degrees, you're really looking at heat pumps or other low temperature technologies. So 100 to 550 is our sweet spot.
And we'll note from that study that was mentioned earlier, the Arena ITP study, there is quite a few, a bit there in that study. You'll see 250 degrees to, I think, 500 or 800. We see there's not a lot between 250 and 800, apart from that power generation opportunity. Most processing is 250 below or 800 above when you get into calcining things. So it looks like you guys have got a fair bit covered there. That's great. I'd like to jump to the space requirements there. Tom, you answered a question there for Satinder. I'm not sure if that was, let's just double check, 10 megawatt thermal capacity, as in 10 megawatt delivered. You said 15 square meters for Rondo, or was that for 1 megawatt thermal capacity, Tom? Oh, just on mute there, buddy.
Sorry, it's not just my microphone. Yeah, the 15 by 15 is in that 10 megawatt boiler capacity range, and we have a larger product which is about 3 times larger, and that delivers up to 30 megawatts.
Okay. So 30 megawatts. Got you there. Will any indications by that one? Tom said 15 by 15 for 10 megawatt thermal. Make that 225 square meters. But Will, what about you for 10 megawatt or so thermal capacity?
Yeah, I'll come back to that before we end the call, but I'm just going to run a quick calc and find the number and come back to you, Jarrod.
No worries. Good. And there was that comment there, and Tom, you addressed that one pretty quickly, that heat is the primary use for this. Electricity is a secondary application, and not quite getting to that one at the moment.
Yes, just to add to that, like our portfolio is probably like 2/3 heat only, a quarter heat and power, and then very, very small amount is power only. And I'm more skeptical about that application than the other two, just because of the poor efficiency that you get.
Gotcha. Ian, if I could bring you in, a question there. You quoted $50 a megawatt hour for LV on that fabulous solar circuit tariff that we can only dream that gets rolled out throughout Australia. Well done, Essential. What about HV? Would you have a guess at any numbers if someone was just doing an HV connection there?
Yeah, great question. And yeah, part of the trials is making sure tariffs that we're calculating are fair and equitable for all customers. So indicative pricing, I think I mentioned on the slide, for LV could be somewhere between $30 a megawatt hour and $50 a megawatt hour for purely dynamic access to the network. So we're not adding to peak demand. HV would be less again on LV. So going back to the slide where we break the network into sub-transmission, HV and low voltage, effectively if you plug into higher levels of the network, pricing structure would be less. So we have customers connected right across those 3 layers, depending on the size of the load. And I think what I am seeing in the market, particularly with the larger eTES units, there is interest to connect direct HV. So probably more relevance for an eTES or larger eTES units would be the HV type tariffs. And we're looking at both large LV and HV tariff innovation as part of these trials as part of the electrification program.
Brilliant. Thanks, Ian. As you're seeing from what Tom presented, network charges, this is all going to be about network charges. If everyone will be able to use these to charge in the middle of the day with very low wholesale prices, then this is right. How do we get that network charge down? So yeah, that sounds good.
Can I just jump in there on that? the HV charges. So your typical, depends on the state, but most of the states, if you've got a large customer tariff transmission connected, it's like $25 a megawatt hour. So it's, half the price of even the best distribution connected. And then some of those, there are special tariffs within that I think the lowest we've calculated is equivalent to about $5 a megawatt hour. Not entirely sure if that's something we can sign a piece of paper on, but that's looking what the indication is at the moment.
Thank you. And Tom, there was a question on doing high voltage. You said you're okay at high voltage. I mean, maybe it's going to be
depends what high voltage to me is, like hundreds of kV. But we've certainly had had some funky US voltages in the past that customers have complained about, and we're bumping those up and standardizing it with the Australians. So moving towards standardizing on 11 kV, for instance, because a lot of people already have that on their site.
Right.
Something you can buy equipment off the shelf for. So,
and will MGA, you guys headed towards 11 kV or 22 yourselves?
Yeah, that's right. It seems to be a pretty and it sounds like, Tom, you're experiencing similar things as well. This is one of the big challenges. I think Ian, you mentioned earlier that the technology is quite simple, and I think very quickly we're going to move away from technology risk once we can get the first few commercial projects up in Oz, to then the network challenges and integrating at high voltage. So yeah, absolutely right, Jarrod. That's the goal. Just on that footprint point as well, to come back to a good number for our system is 250 kilowatt hours per meter squared. So that sort of gives you a nice baseline that you can use to estimate the footprint for your system.
250 kilowatt hours per meter
squared.
And what's your usual delivery ratio to storage? So if you had a 1 megawatt of delivery of heat, are you going to be storing 10 megawatt hours or 5? What's your ratio there going to be? Well,
yeah, it's a good question, and to be honest, it varies a lot. So when we look at like a large mining operation that's operating 24/7, then generally, if you have a steady state load, you'd need at least 16 hours of storage. The remaining 8 hours of the day, you're simultaneously charging and discharging. But then for other applications where, think for example, a dairy farm, which might have a more peaky load, then, maybe 6 hours of storage is enough to really get an economic use case. And that might tackle, the most expensive part of your energy needs. So it really fluctuates a lot. We seem to, commonly land in the middle with about 10 hours of storage. So.
Gotcha. Those meat processing plants, they usually need about 10 hours a day of heat, so that should work well with these sorts of systems. Nice. Ramp up and ramp down times. Tom, Will, maybe you're up. You want to answer that first? How quickly? I think you did mention it briefly, but how quickly can you ramp up from with one of your systems from zero heat to thanks for the steam?
Yeah, so on the steam generation side, we just use a standard off-the-shelf HRSG from a leading brand like Alfa Laval. We can essentially ramp that power output at about 25% per minute, so really quick to respond. On the charging side as well, it's as quick as a lithium-ion battery. It's basically a big resistor bank that we can respond in less than 100 milliseconds to different control signals, which really unlocks a variety of grid services as well. But yeah, how about you, Tom?
Pretty much the same. Our technology is too similar, mate.
This is good. It gives confidence that we can compare and understand it. I mean, and that's a funny thing you mentioned there, Tom. But I know you've gone for sort of the dirt cheap, and MGA's got a bit more tech in there in terms of and maybe higher connectivity. But we'll see. It's going to be horses for courses. It's good to have both of you competing and working to try and find these solutions. I'm sure that's a great outcome for decarbonisation and our manufacturers. So good stuff.
Absolutely.
Nice. Look, I think that's we're getting a bit short on time. It's probably time to start ramping up. There was a question on what can governments do. So I thought we might do a couple of poll questions here. I've just got the two for everybody, and let me launch the first poll here just to test the flavour. While we've got so many people in the room, I thought it'd be a good opportunity to test the flavour on on this eTES and how applicable it may be to your site after seeing this and getting a bit better understanding. Maybe you need some more info, and by all means reach out to them individually. We'll make sure you get Tom and Will's email addresses for sure as when this the presentations are emailed out to you. Hey, but look at that, gents. Got to be happy with that. And Laura, looks like we had an appropriate webinar then if this is applicable. Nice. Good. Thanks. Still a couple more coming in. I've got one more question for you that'll take just a minute longer. Thank you for that. That's come through. I'll share the results. Looks like everyone highly applicable or somewhat applicable. So we're in the right ballpark here. This is good. And I've got one more question here for you, and that's does lead into the comment on what government can do and what others can do as well. Let's see if this one will come up for you. And this is sort of a ranking poll here to see. Let's see what you can what's needed, and it's sort of somewhat put in an order of way you may be looking at this at the moment. Studies, we have heard that often it's hard to come up with that 50 or 100 grand to come up to get that study moving. Will Reeves showed that today that can be helped out with the ITS program. They will help you out with those studies as well. Maybe you need more confidence or more information on best practice. Maybe there's needs more support for CapEx. Will came through already with support for CapEx, so that's already there. Incentives, we've got VEECs and ACCUs and ESCIs. That's there already from New South Wales VEEC, and ACCU's a bit more costly, but still available. How about those electricity prices on the OPEX side of things? Maybe it's that. Or do we don't want to see higher gas prices, but it no doubt would facilitate such a change. So we've got a few answers coming in. Thank you so much. I'll just give it another minute. And while we're before I hand back to Laura, we figure one of the issues you may see this is that electrical connection and having the capacity there. So what we intend to do is in exactly 10 days' time, we're going to hold a webinar of 3 ways to get the most out of your connection and to avoid a transformer upgrade. So that'll be a webinar coming up Monday week on the 24th of February. We're going to have Essential back on to talk about those costs for upgrades, as well as talk about the three different ways of how to avoid that upgrade. And obviously energy efficiency is going to come in there, and load flexing and things as well. Looks like we've got lots of results in from the poll. Let me share those results with you. And okay, there we go. Looks like number one. Looks like Jarrod didn't work out how to understand the poll results before he started this poll. So yeah, good. Look, if anyone can work out these colours and help me out, that'd be great.
Yeah, for sure. Well, thank you, Jarrod. And I'd just like to say again, thank you to all our presenters for their fantastic presentations and sharing all that information. There was a lot packed in there in 1 hour. As Jarrod mentioned, we have that webinar coming up in a couple of weeks. We have some other events coming up. We've got our member drinks and update next week in Sydney and online, and that's exclusively for A2EP members. And we have also just announced our first site tour for the year, which is heading out to a beautiful winery out of Melbourne to check out the heat pump system that they've had installed there, and an award-winning system, and a couple of other stops there too, including Brick Lane Brewery. So check that one out. You can scan the QR code, and we'll also put the links to sign up in the email that we send out next week with the recording and with the slides from our presenters. But for now, I'd just like to say thank you to everyone for joining us. Oh, the heat pump, the heat conference. Thanks, Jarrod. Yes, we've also got the Australian Renewable Heat Conference coming up in August, and we've got the prospectus out for that. We've got links on our website that you can check out. It's really exciting. We've already had packages snapped up for that one, and it's going to be even bigger than last year. So if you're interested in what we were presenting today, please do check that out and keep an eye on announcements of our speakers and the program, which will be coming very soon. So thank you again for taking the time to join us. We'll wish you a good afternoon. Thank you.